Let's look at the Charles law. Let me take this out. Now, in Charles law, we say the volume of a given mass of gas is directly proportional to its temperature in Kelvin if the pressure remains constant. In the Boyle's law, the temperature was constant, but in the Charles law, the pressure is constant. So, in that case, let's look at it mathematically, then we see what we have. So we say that the volume of a given mass of gas is directly proportional to its temperature in Kelvin, which means V is equal to KT. This is the mathematical constant. If I make my constant the subject, I will have K is equal to V over T. So this is what we have. Now, how do I explain this? They say that the volume is directly proportional. Kinetically, according to the kinetic law or explanation, it means that when the volume of a given mass of gas increases at constant pressure, the temperature will increase, and vice versa. So this is the mathematical explanation, which means that V1 T1 is equal to V2 T2. So this is how this law goes, and so on and so forth. So let us see by solving one or two questions. Diagrammatically, it means the same thing, that the volume is directly proportional to temperature. Directly. So as this one increases, this increases, and that tends to continue. So in all ramifications, when your volume increases, your temperature increases. So let's take some calculations. Question 1. So we have V over T. Take note, we don't forget this. So question number 1 says, the volume of a fixed mass of gas measured at atmospheric pressure, measured at atmospheric pressure and 27 degrees Celsius is 3.0 dm3. We should calculate the volume at blah blah blah. Let us find out our values. The given is always this way. Sorry, let me shift this a little bit down this way. So V1, T1, V2, T2. Remember, V over T. So we go. Let's take the question now. The volume of a fixed mass of gas measured at atmospheric pressure and 27 degrees Celsius is 3.0 dm cube. So V1 is 3.0 dm cube. 3.0 dm cube. And the temperature therein, let's say, is 27 degrees. T1 is 27 degrees Celsius. Okay. Calculate the volume, V2, at 127 degrees Celsius. 127 degrees Celsius. And at the same pressure. So the pressure is constant. Remember, I talked about the real value for temperature, that the temperature, the official value is in Kelvin. Okay, unless if you're asked to leave your answer in degrees centigrade, then you can leave it there. But if you are not asked, you have to take it to Kelvin, because we say the volume of a given mass of gas is directly proportional to its temperature in Kelvin. Okay, provided the pressure remain constant. So we have to convert this to our Kelvin scale. And we say, for us to convert it to our Kelvin scale, we have to add 273, okay, which is the standard value for temperature. So now, we want to do that. So let's say, if I take this as a plus 273, put my K, I'm just trying to follow the rules here, plus 273, put my K. So this will give me I have 27 plus 273, that gives me 300. So 300 Kelvin. 127 plus 273 is 400. So I have 400 Kelvin. Now, the law or the formula says V1 T1 is equal to V2 T2. We are looking for V2. So my V2 is equal to V1 T2 over T1. And this is equals to, in case we don't understand, we cross multiply. This times this is equals to this times this. So we have V1 T2. We divide both sides by T1. That is what is left. So my V1 is 3.0 dm cubed times T2 is 400 Kelvin over T1 is 300 Kelvin. This is equals to, so I have 3 times 400 divided by 300. It's 4. So I have 4 dm cubed as my final volume. So that's our first question. Let us move on. Question number 2. A given mass of gas occupies 500 cm cube. 500 cm cube. At 25 degrees Celsius, T1, 25 degrees Celsius, so let's say plus 273. Okay. Calculate the temperature in degrees Celsius at which its volume doubled at constant pressure. So the volume doubled. If it was 500, it would become 1000. So they say we should calculate the temperature in degrees Celsius. Remember I said the official value is in Kelvin. So when we are done having our answer in Kelvin, we minus 273. We take it back to the Celsius scale. So from here, the formula says V1 T1 is equal to V2 T2. But then we're looking for T2, so T2 is equal to T1 V2 over V1. And this is my T1, which is 25 plus 273 is 298. So this is 298 Kelvin. So I have T1 is 298 Kelvin times V2 is 1000 cm cube over V1 is 500 cm cube. So if I have my 298 times 1000 divided by 500 is 596. So T2 is 596 Kelvin. If I minus 273, I will be left with, because I have to take it back to the Celsius scale, minus 273. 323 degrees Celsius. So that is my answer, because I was instructed to leave it in the centigrade scale. Okay, let's proceed to the third question. It says a gas sample with initial volume 3.25 dm cube, 3.25 dm cube, is heated and allowed to expand to 9.75 dm cubed. 9.75 dm cubed. At constant pressure. What is the ratio of the final absolute temperature to the initial absolute temperature? So this is important. So we're looking for the ratio of the initial and final temperature. So this is all that is given to us. So remember, before we get into the business, let me give us a scenario of comparison. If I have A over B is equals to C over D, according to ratio, it means that A is equals to C, A is over C, this, and this is equals to B over D. So this over this equals to this over this. In ratio is the same thing. So if this is true, let us compare with what we have. We have V1 T1 is equals to V2 T2. If this is true, that also means that V1 over V2 is equals to T1 over T2. And this is, V1 is 3.25 dm cubed. Is to ratio of V2 is 9.75 dm cubed. Remember, that is equals to this over this. So according to ratio, we divide by the smallest. So this is over 3.25 dm cubed. 3.25 dm cubed. So this is obviously 1:, we'll come back here, we have 9.75 divided by 3.25. This is 3, approximately 3. It therefore means that 1/3 is equals to T1 over T2. So the ratio is 1:3. So that is what they are asking of us. So that's all. Let us move on. Question what? 4. Okay. A fixed mass of gas of volume 546 cm cubed. 546 cm cubed. At 0 degrees Celsius. 0 degrees Celsius plus 273 is equals to 273 Kelvin. Is heated at constant pressure. What is the volume of the gas at 2 degrees Celsius? 2 degrees Celsius plus 273 is equals to 275 Kelvin. Sorry. No, that's not it. They say, what is the volume? So we're looking for V2. That's not supposed to be there. What is the volume? The air is 2 degrees Celsius. So we just add our 273, which is 275 Kelvin. Okay. That's true. Let's proceed. We have our formula. V1 over T1 is equals to V2 over T2. So we're looking for V2. So V2 is equals to V1 T2 over T1. And this is equals to V1 is 546 cm cubed times T2 is 275. 275 Kelvin. This is over T1, which is 273 Kelvin. And this is equals to 546 times 275 divided by 273, 550. So this gives us 550 cm cubed as our final volume. Let's take our fifth question. Our fifth question says, a fixed mass of gas occupies 40 cm cubed at 0 degrees Celsius. So we have our V1 and T1. Let's take out this. A fixed mass of gas occupies 40 cm cubed. This is 40 cm cubed. At 0 degrees Celsius, T1, 0 plus 273, does give us 273 in Kelvin. Find the temperature at which its volume becomes 54.7. Volume becomes 54.7 cm cubed. Assuming that its pressure remains constant. So we're looking for T2. We go again. V1 T1 is equals to V2 T2. We're looking for T2 here. So our T2 is equals to T1 V2 over V1. And this is equals to T1 is 273 Kelvin times V2 is 54.7 cm cubed over V1 is 40 cm cubed. And this is equals to, our T2 would be 273 times 54.7 divided by 40, 373 Kelvin. Okay, we'll take, that's the fifth. Let's talk about seven, the seventh question, probably. 6 now. The sixth question says, a certain mass of gas occupies 300 cm cubed at 35 degrees Celsius. 300 cm cubed at 35 degrees Celsius, so we'll add 273 to take it to Kelvin. Okay, at what temperature will it have its volume reduced by half? At what temperature will the volume of this reduce by half? So if you reduce by half, that becomes 150 cm cubed. Now, the formula says V1 T1 is equals to V2 T2. We're looking for T2 now. So T2 is equals to T1 V2 over V1. And this is equals to, what is T1? Oh, sorry, let me add that. 35 plus 273. 273 is equals to 308. So this is 308 Kelvin. So my T1 is 308 Kelvin times V2 is 150 cm cubed over V1 is 300 cm cubed. And this T2 becomes 308 times 150 divided by 300. 154 Kelvin. So that is our sixth. Oh, is that a seventh question? Okay. 300 at 35, at what temperature will it have its volume reduced? Okay, that's our sixth question, I guess. Let's take the last question on this. A sample of gas has a volume of 500 cm cube at 45 degrees Celsius. What volume would the gas occupy at 0 degrees Celsius when the pressure is constant? A sample of gas has a volume of 500. V1 is 500 cm cube. At 45 degrees Celsius, T1 is 45 degrees Celsius. So I just want to take this out and add my 273, and that will give me something in Kelvin. What volume would the gas occupy, V2, at 0 degrees Celsius? 0 plus 273 Kelvin. When the pressure is constant, pressure is always constant. Okay, I have my 45 plus 273, 318 Kelvin. So V1 T1 is equal to V2 T2. I'm looking for V2. So V2 is equal to V1 T2 over T1. And this is my V1 is 500 cm cube times my T2 is 273 in Kelvin over T1 is 318 in Kelvin. And that final volume is 500 times 273 divided by 318, 429. 429 cm cube. Okay, that is that about the Charles law.